Okay, so it's a pleasure to introduce our final speaker of the workshop, Vera Tonic, live from Croatia this evening, for her anyway, telling us on alternative proofs for the n-dimensional resolution theorem in dimension theory. So take it away, Vera.
Thank you, Craig. So thank you to the organizers for giving me this opportunity to give this talk. And I guess traditionally, if this is the last talk of the workshop, this would be the time to give a round of applause to all the organizers, but online it's kind of hard to do. So we can pretend to do it virtually. So anyway, thank you very much for giving me this opportunity, and great job, everybody who participated in organizing this. So this is a joint work with Leonard Rubin, who is also here. Glad to see you. And the plan of my talk is going to be this. First, we will review some basics about resolution theorems in dimension theory, and we'll tell a little bit about the original proofs of those theorems, and then a little bit about this idea of possible alternative proofs of resolution theorems for groups Z, Z mod P, and Q in a unified approach. So first, I'd like to explain the meaning of the word resolution because it's used in mathematics quite a lot. So here it refers to a map, which is going to be a continuous function for us, which is between topological spaces where the domain is in some way better than the codomain, and the fibers or point preimages of a map meet certain requirements. And the reason why X is the codomain is because that's where you start. You start with the codomain, and then you build a domain with some better properties, and maps the map between new domain and the old codomain should have some nice fiber properties. And the resolution we obtain will start with X, which has dim G, cohomological dimension modulo abelian group G, bounded by some number. And then the goal of these theorems is to obtain Z of finite dimension, and the map between Z and X should have cell-like or G-acyclic fibers. And if you can see, I don't know how well you can see this, there's a slight change of color in these notions because those are the notions which I would like to define for you, or at least remind you of the definition. Before then, I need to say that domain and range for us are always compact metrizable spaces. All our spaces are compact metrizable, and our groups are all abelian. Before I continue, though, I want to say I'm not going to give you the original definitions for dim G. Well, the definition for covering dimension you probably would need anyway. Instead, I will characterize these notions in terms of extension of maps. So the next thing I mention is going to be a reminder of a definition of absolute extensor. So a topological space Y is an absolute extensor for a topological space X. For me, it's better to say X is an absolute coextensor of Y because it preserves the direction where the map is going. If for any closed subset A of X and any map from a continuous function from A to Y, you can continuously extend it over the entire X. And the notation we will be using for this is going to be this bottom notation, X tau Y. So that means X is an absolute coextensor of Y. This is Kuratowski's notation to honor Tietze. So given that, I can use characterizations of both dim and dim G. So I will just read dim G instead of cohomological dimension modulo abelian group. But in any case, here are the theorems that give you alternative definitions. So for compact metrizable spaces, if n is a natural number of 0, you have the following to be true. Dim of X, covering dimension of X, is bounded by a number n if and only if X is an absolute coextensor of an n sphere. And for KGN, or for dim GX, you have this dim G of X is bounded by n if and only if X is an absolute extensor for KGN, where KGN is an Eilenberg-MacLane complex of type Gn, which means it's a connected CW complex, at least it's connected for n greater than or equal to 1, which has the property that its nth homotopy group is isomorphic to G, and all other homotopy groups are trivial. So for the general correspondence, again, only for compact metrizable spaces, so it works here. For the general correspondence between dim G for any abelian group G, dim Z and dim, you have this inequality above. So dim G of X is less than or equal dim Z of X less than or equal dim X for the same X. But if dim is finite, then dim Z and dim are the same. That was a theorem by Alexandrov. But there are examples of compact metrizable spaces which have infinite covering dimension and finite dim-z. First of those examples is due to Dranishnikov from 1988. There's another by Didak and Walsh. Okay, now we are going to go and define cell likeness of a map, and there's several ways of defining this. The easiest way to imagine it is to say, well, a map is cell-like if point preimages or fibers are cell-like sets, and a cell-like set is a generalization of contractible sets. So if you want to think about an easy example, you can think about a map with contractible fibers. But to officially define it, you could use this third line here. So what you want to say is, so the point preimage or a fiber for any X will be cell-like if you take any CW complex and any map F from that fiber to this CW complex, that map is going to be null homotopic. Now, in this theory, we use inverse sequences quite a lot. So if you can represent your fiber as the inverse limit of an inverse sequence of compact metrizable spaces, where the bonding maps are null homotopic infinitely often, maybe not all of them, but infinitely often they are, then again, you can claim that this is a cell-like set. Okay, and then for GA cyclicity, the notion of GA cyclicity is a generalization of cell likeness. And the original definition would be, you want your fibers to be so-called GA cyclic sets, or have the property of GA cyclicity, which just means that they have trivial reduced Čech cohomology with respect to the group G. But again, you can use the following. If you take any map, a continuous function from a fiber to a KGN, then you want that to be null homotopic. And again, if you represent your fiber as the inverse limit of an inverse sequence of compact metrizable spaces, and if you can guarantee that infinitely often your bonding maps will induce zero homomorphism on the level of cohomology groups, then you can guarantee that this will be GA cyclic. And just to emphasize for comparison, since in the definition, one of possible definitions for cell likeness, you had maps going from your fiber to any CW complex, and in GA cyclicity, you had your maps going to KGNs, then you can see that cell likeness of a map implies that this map is GA cyclic. Okay, so now the first official resolution theorem in this list, there will be a list of 4, is due to Robert Edwards and John Walsh. And it says, it's easiest to follow on the diagram. You can, if you start with a compact metrizable space X, of which you ask that its dim Z is bounded by a natural number, then you can come up with the Z, which is a compact metrizable space whose dimension, covering dimension, is bounded by the same N that showed up below. And you can build a map between them, which is cell-like. And this is important because, remember, Dranishnikov's example gives you existence of compact metrizable spaces whose dim Z is finite, but covering dimension is infinite. So the fact that you can produce this Z with finite dimension, together with this theorem, gives you the fact that a cell-like map can raise covering dimension. And then the next theorem in this line is due to Dranishnikov, and basically says the same thing, except that dim Z from before is now replaced by dim Z mod P, and cell likeness is replaced by Z mod P acyclicity of a map. And then the third theorem in line for group Q, due to Misha Levin, the difference is now that you're expecting N to be greater than or equal to 2 because there's a counterexample for N equals 2, for N equals 1, so you start at 2. But again, otherwise, the theorem sounds like those before, except Z mod P or Z is now replaced by Q and Q acyclicity for the map, which could lead you to believe that this should work for any abelian group, right? Just replace Q by any abelian group G, but in fact, that's not quite the case. For example, quasi-cyclic P group, which is listed here, is such that if you try to put this instead of Q or Z mod P or Z, you cannot really achieve this dim Z to be bounded by N, but at most you can achieve that it's bounded by N plus 1. And in fact, this group is included in the general resolution theorem, which works for any abelian group, which is again due to Misha Levin. And for that one, you can really put any G abelian here and into G cyclicity, but the best you can do for your dim Z on top is that dim Z is bounded by n+1, and dim G of Z is still bounded by n. So this space is still at least as good as that one, possibly better. Okay, so I'd like to tell you a little bit about original proofs of these resolution theorems, but first I would like to mention a couple of facts. These theorems, the four ones that I mentioned, but we will be particularly interested in the first three, they are all based on, well, they start by representing your compact metrizable space as the limit of an inverse sequence, which is nice enough. So the guarantee that you can do that is the Freudenthal theorem that I have mentioned here. So every compact metrizable space can be represented as the inverse limit of an inverse sequence of compact polyhedra with nice bonding maps. I could explain the nicety, but we really don't have to. And another theorem I'd like to mention is once you have an inverse sequence whose members are nice enough, then the limit is going to be nice enough also. So this theorem is saying in the form that we needed, if you have an inverse sequence of metrizable compacta, then the limit is also going to be a metrizable compactum. If all the members of your sequence are connected, then the limit is also connected. If they are non-empty, the limit is non-empty. And if dimension of each member of your sequence is bounded by some number, then the dimension of the limit is also going to have the same bound. Okay, now let me tell you a little bit about the general idea of proving resolution theorems in the original form. So you start with a compact metrizable space, which has some required property, dim G of X less than or equal N, for whichever G. Yeah, you choose an inverse sequence that of compact polyhedra whose limit is X with maps nice enough. And now your goal is to use this inverse sequence as a foundation, in some sense, as a source, to build another inverse sequence above it. Let's say it's above for the sake of this picture, together with an almost commutative ladder of maps. I mean, I realize that the ladder is maybe not the best metaphor for this because it's not leading up, it's just lying down on the side. But okay, let's just call it a ladder of maps. So this is not quite commutative, but it should be close enough to commutativity. And if you can achieve that it's close enough to commutativity, it will help you for this map Z from Z to X, let's call it pi, for this map to be produced. And if you carefully choose the properties of your G's on top, these blue maps, then you will be able to get good fibers for your pi. But yeah, one more thing. So the bottom sequence is pre-chosen, and then you gradually build whatever you have on top here. And it's kind of carefully built with using factoring maps through something, with changing triangulations as you go. And the hardest part of this construction is producing these suitable maps on top, because like I said, very vaguely, from their properties are the source of good fiber properties for your vertical map here. So the hardest part of the construction is producing these suitable maps. And the way they are produced is by factoring these maps on the bottom through certain geometric objects, which are built based on algebraic topology properties that you wish. And those, for example, for the group Z are called Edwards-Walsh complexes. And they are fairly complicated because in building them, you start on a skeleton here, and then you attach KZNs to some simplices into it. In it, and then you attach more cells to achieve more algebraic properties. So even for Z, it's not such an easy object to describe. For Z mod P is a little harder, and it doesn't quite exist in the way it does for Z for all groups, but for Q, you can construct an object very much like it, let's say. But my point here is that these geometric objects, even if you like algebraic topology, get a little unyielding. They get kind of hard to understand. So the motivation for our work here is, first of all, can we replace these geometric objects with something possibly simpler? something easier to understand. And then can we put together the proofs for groups Z, Z mod P and Q together so that the geometric objects that we use are kind of easy to explain for all of these three things. I mean, separately, you would attach different attachments, but the main idea would be the same. So this is work in progress, I have to warn you. So let's pretend for now the answer is yes. We have to double check it. So here's what we did. We start again with the compact metrizable space, which has some requirement of dim G of X be bound by an N, where G for us is either Z or Z mod P or Q, because we're only dealing with these three groups. And what we do differently than our predecessors is we embed X into the Hilbert cube. And I'll just point out here that it will become important for us what are the notation for our projections from a larger part to a smaller part of Hilbert cube. And we can do it in such a way that there exists an increasing sequence of n's, which will give us increasing pieces of Hilbert cube. And in these increasing pieces of Hilbert cube, we'll be able to find compact polyhedra. And for them, what we will achieve, and I'll show you the statement of this lemma in a picture because it's easier to follow, what we will be able to achieve with this polyhedra is the following. We want when you take each of these polyhedra and multiply by the rest of the Hilbert cube, we want the intersection of those objects to give us X. And this is doable. And it's also doable in a way that if I have a polyhedron in a larger part of the Hilbert cube, I can project it to the polyhedron in the smaller part of the Hilbert cube, and this projection should live in the interior of the previous polyhedron. So the projection of that to the smaller part of Hilbert cube should live in the previous polyhedron. And this way, in fact, I can build an inverse sequence of these polyhedra, and the maps between them are really, the bonding maps between them are projections in a Hilbert cube, but just restricted to the polyhedra. And so I will use this as a base of building things. So based on this inverse sequence, we would like to produce an upper inverse sequence for our ladder of maps. Now, this ladder is even more complicated, so the metaphor is even worse, but bear with me. And we will again need to use factoring maps through geometric objects, but geometric objects will be simpler than Edwards-Walsh complexes I mentioned before, and they will be easily adaptable for a choice of CW complex K. This K will replace either KZN or KZ mod PN or KQN. And this proposition that I now mention is the one that is fairly large, but I'm only giving you a basic outline of it. It's telling you how to produce the map in the upper inverse sequence, or at least prepare to produce it. And this is a proposition that uses a particular geometric object that we used. And that was the easiest thing for me to show you, because that's the easiest part to explain. So if the proposition is saying this, if you have a map which is, say, nice enough, whatever that means, between two polyhedra, but the polyhedron in this picture on the left is already triangulated, and if you take K to be either KZN or KZ mod PN or KQN, then here's what you can do. The geometric object you build initially is called FLK, and this will consist of this L, which is a triangulation of this other polyhedron. And then you notice all n+1 dimensional simplices in it. And to each of those, you attach a copy of K. Remember, K is either KZN or KZ mod PN or KQN, whichever one you need based on the group you were given. And once you attach it, you think, well, that's great. That's easy enough to understand. But in fact, you will not need the entire object. You will only use what we call FLK star, which is just going to be a CW complex built like this. Out of your original FLK, you take the n skeleton, and then out of every hat that you built, that KZN or whatever you attached, you only take the n+1 simplicial, CW skeleton of it. So you take only cells up to n+1st dimension. So this is a much simpler geometric object, and it still has algebraic topology properties that we need. And in fact, the rest of the lemma is telling you, okay, I can use this object to produce a certain triangulation here and to be capable of building a map with nice enough properties for what we need. Now, I'm hiding a lot of things here, a lot of technical details, but in essence, I just wanted to point out what the geometric object looks like that we are using. There's a price to pay for using simpler geometric objects, which is a lot more technicalities to satisfy. Okay, now when we apply this above mentioned proposition to the original inverse sequence of these polyhedra, by the way, we will not apply it every step of the way. We'll have to skip and jump through the sequence, but it's doable. We will also need some technical lemmas that tells us in this new ladder of maps that we're building, how close or far apart things are allowed to be in order to get whatever it is that we need to get. But remember, the original proofs of resolution theorems, they also needed some technical conditions to build the map pi from Z to X. So there we are not really different. And my final slide is really kind of an overview of what I was calling a ladder of maps in this proof. So if you remember, when you start with the X, then you write your X as an intersection of these objects which contain polyhedra in them. Then you focus on just the sequence of polyhedra with projections or restrictions of projections between them. And then you look at certain triangulations and certain subdivisions of these triangulations. And here, let's say, you apply that proposition that I mentioned. So there's some bit of geometry hidden here. This helps you build the appropriate map. You do something else to this map in order to produce the blue map on top. But now notice that these blue maps, whichever nice properties they might have that I'm not mentioning, they're also working between n+1 skeleta of some triangulations mentioned below, which means that every member of your sequence on top is an n-dimensional. So your Z, in fact, is going to be n-dimensional also. And here is where you get your map pi. And this is going to be all for me. Thank you.
Okay, we got time for questions if anybody has some. Any questions for Vera? Okay, well, let's thank her one more time.
Thank you.